So at the very beginning, we need to know some definition, and maybe already some of you already know these definitions, but let's do a very quick review. So the first one is the precipitation, and I'm sure all of you already know about that. Rain is a part of precipitation. So basically the precipitation is any product of the condensation of atmospheric water vapor that falls under gravity. And the main forms of precipitation include drizzle, rain, snow, etc. Okay. Now the drainage area is like, if you look at this picture, like this watershed or like these two, okay, so you will see there is one main stream and there are some like tributary here. The same thing here, we will have a main stream and some of the tributary. These are actually the river or canal system in a watershed. So the whole thing is called the drainage area, and it is defined as the land area where precipitation falls off into creeks, stream, rivers, lakes, and reservoir. It's like which area we are considering to calculate the total runoff. Okay. Now, obviously, the next definition is runoff. So, in easy word, runoff is after any storm or rainfall when soil can't take enough water, the excess water will run over the surface, and which is called the runoff. So a good definition will be that water that occurs when excess stormwater, meltwater, or other sources flows over the Earth's surface. Okay, there can be several reasons of this runoff. It can happen because the soil is saturated to full capacity. It can happen when rain arrives more quickly than the soil can absorb it. It's like the capacity of soil can absorb is actually less than the rain era, like the total amount of rainfall is coming. Or another reason can be if all the areas are actually covered with like roof or pavement, like the impervious area. So there is no way water can go through this impervious area. So these areas send their runoff to surrounding soil that cannot absorb all of it. So basically this is the problem for the urban area where we have lots of impervious areas. Okay. Now the next term is actually the peak runoff. So if you look at this picture, here is the time from beginning of storm, and this one is the rate of runoff or rate of discharge. As a whole, this graph is called hydrograph. We will learn about this hydrograph in next 2 or 3 classes, okay, maybe. So here, if you look at this point, when at the very beginning, the rate of runoff is 0 because all the water is actually going through the soil. But with time, you see the runoff is increasing, and at some point it becomes stable, and after that it starts decreasing. So the peak runoff is that the maximum rate of discharge during the period of runoff caused by a storm is called a peak runoff or peak flow here. Okay. So maybe after that time, rainfall stopped, and then slowly the runoff is decreasing as well. So for this part, like module 3, basically we will cover the calculation of peak runoff, like how can we calculate the peak runoff using different methods. And at the very end of this module, we will design a storm sewer which can carry the peak runoff. Okay. Now, for calculating the peak runoff, the time of concentration, to know about the time of concentration is very, very important, as I said earlier. So let's discuss a little bit about time of concentration. So time of concentration is actually the time at which the peak flow will happen. Okay, so if I try to draw that, like from this point to this point, that is actually the time of concentration. And after that, the storm will stop and the flow of runoff, like it will start decreasing. Okay, so we will discuss about the time of concentration for next few slides. Here, as I said at the very first slide, where we discussed the watershed, that water is coming from different point. So this is a setup in your lab where you were supposed to do a lab called rainfall runoff. So from this pipe, you see the this pipe. So this will actually deliver the artificial rain, and from this point, water will come as like river flow. Okay, so there will be a river flow and there will be rainfall, and that is the outlet from where you will collect the water. So with time, like when there will be rainfall from this point, this point, this point, this point, from every point, water will come eventually to this point. So the time of concentration is actually time at which all parts of the watershed begin contributing to the runoff from the basin. And it is also the time required for water to travel from most hydraulically remote point in the drainage area through the drainage area outlet. Okay, so we already know at time of concentration the peak runoff will happen. So you will know from this part, like when you collect the runoff, like when the peak runoff will happen. And one thing you need to know, this time of concentration, it's not about distance, it's about time. So if I consider like this point, or this point, or this point, like there are 4 different points here. So from which point it will take the maximum time to reach the water to get into the outlet, that is actually the time of concentration. So make sure you know that it's not about distance, it's about time. The next slide will help you to understand the basic of time of concentration. So suppose that is a watershed here, and this is the outlet, and you are seeing like T1, T2. So T1 is actually the time when the water from this like shaded area is coming to outlet. T2 is the time when all the water from this area is coming to the outlet. Okay, so for T1, suppose the area is 45 acres and the time it takes from the farthest point to go to the outlet is 27 minutes. So after a few minutes, this water is coming from this point, and this point. Now the total area covered is 55 acres and the time is 32 minutes. Okay, so those are the maximum point or farthest point from the outlet. Now, when the water is coming from point A and the total area is 67 acres, and in total time it takes 40 minutes to reach an outlet. So in between these 3 cases, obviously the T3, that is actually the maximum time, and that is actually the time of concentration, which is 40 minutes. Now, as I said earlier, it is not about length or area, it is about time. So for any reason, suppose for the soil type or the resistance by the soil surface and everything, it can be the case like the distance is like the distance from point A to B is not the maximum distance. but if it takes the maximum time, that will be the time of concentration. So for this case, this one is 40 minutes. Now, just to give you a better overview about time of concentration, since it's the time, and it's a time, actually the time is the summation of travel time for sheet flow, shallow concentrated flow, and open channel flow. And this is according to the National Resources Conservation Services, like uh, uh, they actually proposed this one, that time of concentration will be the summation of time for these three different type of flow. Now we need to know what is sheet flow, what is shallow concentrated flow, and what is the open channel flow. We already know about this part. Now if you look at this picture, when the runoff coming from roof after any rainfall, obviously this is impervious, water can't go through the roof. Eventually it will come into soil through the gutter. Now at this point, the gutter flow or the lawn runoff, that will be a flow with very, very, very low depth of water. So it will flow like a thin sheet. That's why it's called the sheet flow. Now, once all of this flow comes to the street and from other source water is coming into the streets, so the depth of flow will increase a little bit, and that time it's called the shallow concentrated flow. And after this, all the water will go through like this hole, and water will flow through this storm sewer. Inside the sewer, obviously the flow is open channel flow, and eventually it will come to a local stream, creeks or rivers in the bay. So the time required from like this point, like this gutter runoff to this point, that is actually the time of concentration for this case. So at the end of this class, we will see some video like what it looks like, the sheet flow and the shallow concentrated flow. But for the time being, we can say the time from this point to this point is actually the time of concentration for this area. Okay. Now, let's discuss how can we calculate the time, okay, for each type of flow. So for sheet flow, there are several methods, but we will use the widely used method, this one. And this sheet flow can occur for a maximum length of 300 feet. So after 300 feet, usually the depth of flow will increase and the flow will not be sheet flow anymore. So the time required for sheet flow is this one. You already know N, which is the Manning's N. L is the length, so it can be maximum 300 or less than 300. You know the S naught, which is bed slope. The only thing you don't know is P2. So the P2 is 2 years, 24 hours rainfall in inch. So what does that mean? It means if there is a rainfall for 24 hours, the accumulated amount of rainfall within that 24 hours is called P2, provided that the probability of having that amount of rainfall is like every 2 years. In other words, the probability of having that amount of rainfall in every year is 50%. Okay, so that is the P2, and that's how we can calculate the time for sheet flow. And this is a table for N, or you can use your old N table. Basically, you will get kind of same answer and the same N value. Now, the next part is the shallow concentrated flow. So after a maximum 300 feet, flow usually becomes the shallow concentrated flow because the water from other sources will come and the depth will not be that thin anymore. So travel time for that one is TC2 L2 over V2, and this one is like a rearrangement from the velocity equation, which is like velocity equals to length over time, and that 1 over 60 is just to convert the time into minute. So this length obviously we'll get that from the geometry or the flow, and for this V we have to use a figure like figure 16.7. So you can see there are different type of uh, surface here. So if we know the bed slope, we can actually if we know the surface type, we can actually find the velocity. And the very last one is open channel flow. You already know about open channel flow. And the equation for open channel flow is again same, L3 over V3. But this time the velocity, you have to use the Manning's equation. Okay. Now, there is a question like how we will differentiate between open channel flow and shallow concentrated flow. Uh, Basically, it is done by field investigation or sometimes using some aerial photograph. So using these two methods, you can actually differentiate between the open channel flow and the shallow concentrated flow. So once we know all of these, we can add these three together, and that will give us the time of concentration flow. Now